We're looking at functions in week 2 here. I want to work through some problems I have written down and see if we can get a quick intro at least to some ideas that we're dealing with this week and some quick examples of that. So rate of change, increase and decrease. I want to think about what that means, keeping in mind the graph of the function here. So this one was find rate of change of f of x equals x squared plus 3 from x equals 1 to x equals 6, or we could say on interval from 1 to 6. When we talk about a function on an interval, we're talking about a piece of the domain. So these are the x values that it's between right here. We could also say x is between 1 and 6 using inequalities right there. But that's when we talk about where a function is, we're talking about intervals. Is it increasing or decreasing overall on this interval? And this is only average rate of change because this is a curved function, right? But we're looking at the overall slope or rate of change from the beginning to the end of this thing. So the actual picture, if we look at a graph of this, of course it's out here somewhere on a parabola. But we're just looking at overall rate of change of this. What is the rise and run of this thing? So I want to know how much it went up, and I want to know how much it went over when we're going from 1 to 6 on the x-axis. It went over 5, right? The 6 minus 1 is how much it moved over horizontally there. And the vertical part, I want to compare the two y values. So that's y2 minus y1, or f of 6 minus f of 1. Those are the y values involved. So let me calculate those, and then we've got a rate of change. It's increasing, but I want to see what this comes out to numerically as the rate of change. So f of 6, 6 squared plus 3 is 39. F of 1 is 1 squared plus 3 is 4. And this quotient here will give us the rate of change. So that's 35 over 5, or 7. It's going up at an average rate of 7 units per step there. That's the average rate of change on it. That's going to be positive if you're dealing with an increasing function. And that's just the average on this interval, but it is an increasing function in this whole part of the graph. It's actually, this is increasing from 0 to infinity because the graph looks like that. Okay. Rate of change from 1 to 6 is that 7 units. And we're going to look at function operations. Just quick intro to this stuff, keep the video pretty short. But function operations, when you're dealing with regular adding, subtracting, multiplying, and dividing things, we're just talking about doing stuff to the outside of the function, or to the result of a function. So I'm keeping my x squared plus 3 as f of x, and I've got another function here, g of x. We want to find f plus g of 3. Well, that's the result when 3 is input into the sum of these functions. But if you're just adding them up, you can find the result of either one. This is not different from finding f of 3 and finding g of 3. It's the same input into both functions, and we're going to add up the outcomes. So we can do it separately if you want to, or you could add the expressions and then plug in the x. Either way, you're going to get the same result. This is 3 squared plus 3, and g of 3 is 5 times 3 plus 2, and we can put all of that together and get 9 times 12. Comes out to 29. That's the value there. If you did them separately, well, it's just this and this. This part's 17 and this part's 12. They add up to 29. So you can do it separately or take them apart. When you're adding or subtracting functions, you can do them separately, or you could put the expressions together. F plus g of x is just saying to add those expressions together. So that would be x squared plus 3 plus 5x plus 2. You could combine some terms a little bit there, but that's just the expression of adding those two functions. It's just adding the two expressions. Here I've got a quadratic and a linear, and the other problem here is asking us to find f times g of x, or it might just be written fg. Just means multiply those, but it's of x. So I don't have an input value. I'm keeping x as the input variable. F times g of x is just multiplying the two functions. It's f of x times g of x. just got the expressions for these two things, I'm going to do the multiplying. So that's x squared plus 3 times 5x plus 2. So these regular operations, you just have the same input into both of them, and then you do the operation. In this case, multiplication, I'd have to multiply this whole thing out. That's x squared plus 3 and 5x plus 2. So if I multiply it out, I'm going to have a bunch of terms here. And I get a more complicated function, but that's f of x times g of x. That's what that comes out to. All right. Composition is a very different thing. So it looks kind of similar, except the symbol in here is not one of your regular operations. This is a little O thing, or a little circle thing, but it means of. This is f of g of negative 3. That means something very different from what these other ones did, because we're not using the same input into both here. This is f of g of 3, and the more useful way to write it is, this kind of sounded out what I said there, f of g of negative 3, f of g of negative 3. This would be a more useful way to write that thing. That's what composition means. I've got a function here that the negative 3 is the input into, and then I'm going to take that result and substitute that into the f. So I'm doing f of whatever this comes out to. Got to do it in steps. Now I'm going to do what's inside parentheses first. So this is the function form of do what's inside parentheses first. So let's do g of negative 3. Well, using this function, g of x was 5x plus 2. So g of negative 3 is equal to 5 times negative 3 plus 2. So that comes out to negative 13. So this is negative 13. So my next task is to do f of negative 13. Right, the symbols are helpful here. Not the circle symbol, but writing it out this way is helpful because you do what's inside here. That's a number. That's a value. G of negative 3 is negative 13. Now I'm going to do f of that. So that's my input now into the f function. I got the output of this, and it's going to be the input into the f function. F of x was the x squared plus 3, so I'm doing squared plus 3 with the input now of negative 13. And that's 169 plus 3, so I got 172 for the result there. That's how it looks numerically. If I have an input number, I can just do it a step at a time numerically. If I just have a variable there, g of f of x, I still want to rewrite it this way. The first thing to do is get rid of that circle symbol, which is just going to be confusing, and write out what it is. This is g of f of x. This time, f of x is my inside function. I'm going to take that result and plug it into g, but I don't have a numerical result here, I just have an expression for it. But this isn't the first time we've seen function of some expression in there. F of x is x squared plus 3. So it's g of x squared plus 3. It's not the first time you've seen some function of some expression. We got to substitute this whole expression in to the g function. So that means g of that means 5 times that plus 2. Right? It was this function, it's 5 times that plus 2. But now my input is this whole expression. So be careful about what stuff means. Work your way through it. This is 5 times all of that, so I'm going to end up with 5x squared plus 15 plus 2. Or I can simplify a little bit, but I got that expression. That's that's g of f of x. I want to do it both ways around, so I have this in here. I'm a little crowded. I have f of g of x is a very different thing from g of f of x because it's going to be the other way around, right? This one is f of g of x. This is f of g of x. Very different thing because now I'm doing f of 5x plus 2. Well, quite a bit different because its functions are composed the other way. F of x was x squared plus 3, so I've got to do 5x plus 2 squared plus 3. And you could work that out. I'm not going to finish the simplifying there because that's not that big a deal. But you can see you're going to get a very different expression from what we did this way around. Very different. One of the places we're going to put that to use, Well, you may have already seen some of this, but this is a very big deal in pre-calc, is dealing with these transformations that we have. Horizontal and vertical transformations are examples of this. I mean, I just wrote, well, let me take some simpler ones. Well, I'll use the examples I got right here. If you take the graph of 5 times x squared plus 3 plus 2, the way I have it written here, this is taking an existing function and multiplying it by a 5. That's a vertical stretch. Multiplying the output by 5 is a vertical stretch. And then I'm going to shift it upward by 2. Shift, this is vertical shift, upward by 2 units. So I can think of that graphically. It is a form of composition. When the function is substituted into these things, these are happening on the outside. So I can take that graph and see what happens to the graph of that thing if I stretch it and shift it up by 2. So the regular graph of x squared plus 3 is this parabola that starts with a vertex at 3 here on the y-axis. This transformation of it, stretching it by 5, means it's going to be much further away. It's going to start at 15 and go up much steeper. This thing, much steeper because it's stretched up 5 times as far. All the y values are multiplied by 5. And then if I add 2 to that, so this is 5 squared plus 3. If I do the plus 2 also, it's going to move the whole thing up, just shift it up 2 units. So it's going to start at 0.17. And it's going to have the same shape as this one, but just shift it up 2 units more. So those kind of transformations of the graph, it's a kind of composition of functions.